Our last speaker is Professor Alan Pears. He's a senior industry fellow at RMIT University and also a fellow at the University of Melbourne, and a leading voice in Australia's sustainable energy sector. With over 4 decades of experience in energy efficiency and clean energy policy, he has contributed to national strategies, standards, and programs that have shaped Australia's low-carbon transition. Alan worked closely with Australian Alliance for Energy Productivity, where we advocate the innovative solutions such as heat pumps for decarbonizing building industry. He's widely recognized for his practical expertise, policy insight, and commitment to accelerating sustainable energy solutions. You may actually refer back to some of the challenges that we have in terms of regulations. So that could be a part of the conversation. Without further ado, please join me to welcome Alan.
Right, thank you for inviting me to speak. I have to declare that I'm not an expert on geothermal stuff. In fact, I know a bit about a lot of things because of the wide range of issues that I've worked on over the years. If I go, is that, yeah. Okay, so I'm only going to talk about geothermal in the context of people who are trying to use heat pumps. Okay, so it's a fairly narrow perspective. And I should give a plug. The Australian Alliance for Energy Productivity has a website with a lot of useful webinars. And in fact, last week we ran a renewable heat conference in Sydney, which had 300 people turn up. It was only our second time we've tried it. It was nearly doubled. But the level of interest and the level of practical activity is exploding from a very low base, though. Okay, so what I'm going to do is see what I can talk about. I thought I should start off talking about key factors about heat pumps. And previous speakers have talked about the fact that warmer sources are good for heat pumps. Basically, you can see the curve of the coefficient of performance there relative to the temperature differential across the heat pump. And one of the basic problems we have is lots of people think it's about the temperature of ambient air or whatever you've got. It's actually the temperature difference across the heat pump that drives the efficiency and effectively the output capacity of a heat pump. And what you can see there is that it's not a linear thing. And as you get down to smaller and smaller temperature differentials, the increase in coefficient of performance and capacity for quite small changes in temperature can be surprisingly big. And in that sense, there's lots of games that you can play with heat pumps. Yeah, okay, so I'm emphasizing it's not temperatures, it's temperature lift. If you are dealing with different temperatures, you may want to use different refrigerants relating to the characteristics of the refrigerants, but that doesn't affect the fundamentals of what we're doing here. Okay, so how can geothermal contribute to heat pumps? First of all, as lots of people have talked about, it's a source of heat or cold, which can reduce that temperature differential across your heat pump. It can smooth variable loads because of its thermal inertia and whatever temperature it's at. It can offer thermal storage, and I'll talk about the importance of that in terms of operating costs a bit later. And that thermal storage can be short-term or long-term. There are seasonal geothermal systems around, and there are some interesting creative approaches to geothermal heat use, which I'll talk about in my last slide, as long as I get there. So what are the broader benefits of geothermal beyond the obvious? I was talking to someone from a university in New South Wales, and they were pointing out that when we're cooling our buildings, we're dumping a lot of heat and often evaporating a lot of water and increasing local humidity. So you're getting local heat island effects. So if we are shifting the heat transfer to underground, we actually are potentially reducing local heat island effects and local humidity issues. Also, when the air is very humid, even cooling towers don't work as well. And we see that in a lot of hot, humid climate zones. Yes, so that raises the point that we can actually save some water, and evaporative cooling systems do consume quite big amounts of water. And if you are using cooling towers, you have to use all sorts of chemicals and things because you have to protect against health issues like Legionella and things like that. So if you can get away from those things, there are financial savings, but also insurance benefits and things like that. So it's quite interesting to think about the bigger picture, because often those things are more important to the client than saving energy. You may or may not know that the average Australian business spends energy, electricity and gas is about 1% of their input costs. And that's particularly in commercial sector where you've got high value adding and low energy use, really. So it's pretty hard to make a big argument just about saving energy. You've got to have multiple benefits. And I think the earlier speakers have talked about that a bit. Okay, if we're looking at variable heating and cooling loads, what we find is that it's a real problem for a lot of heat pumps, because due to that variation in coefficient of performance with temperature difference, you can spend a lot of the time having your heat pump running outside its optimal performance space. And so actually you're getting a lot lower efficiency than you might get if you could optimize the performance of the system. So just to give an example here, this is an example of a number of American cities, and the bit that I've circled there is the amount of time that they're running close to peak demand. And the answer is not often, right? So we have lots of people designing heat pump systems for the extreme conditions, and therefore they can be running inefficiently a lot of the other time. So otherwise you've got to have multiple heat pumps or variable speed heat pumps. You can deal with all these issues, but a lot of designers don't because of fairly crude design techniques. And I guess this is where artificial intelligence might help us to actually recognise the costs of running heat pumps outside optimal conditions and then looking at how we can do that better. One of the other big issues is, particularly in cold weather, the issue of icing up. And so if it's cold enough, the heat exchanger of the heat pump will start to not just condense water vapor from the air, but actually freeze it. And so you get the heat exchanger clogged up and you have to run the system backwards to melt the ice. You also may go more aggressively and actually run it backwards to avoid all icing up, but you're losing capacity at a time when the unit is already running at lower output because of the higher temperatures. So this is where, again, whatever we can do to help the heat pump run at a warmer temperature, it's a good idea, and it can save some money. I should also mention that a lot of buildings now actually require heating in some spaces and cooling in other spaces at the same time, where you might have spaces with a large number of people in them and others still needing heating. So we are reaching a period now where for quite long parts of the year, buildings are looking to do simultaneous heating and cooling. Now we can use 4-pipe heat pumps to get both, because when you think about when you're heating your home with your heat pump, if you go outside, you can feel there's pretty cold air coming out of the other side. So the heat pump can provide simultaneous heating and cooling. But I think that's also an area where maybe the geothermal systems can help us a bit. Now, getting on to the electricity market, essentially geothermal systems want to use electricity for pumps and things like that, but also if they're linked to a heat pump, the heat pump definitely needs the electricity. And what we've seen, this is from a couple of weeks ago, a webinar from the NEM review, the National Electricity Market Review. And what you can see is that pretty much all of the year we have big spikes in prices and demand, definitely later in the day and for some of the time also early mornings. These are times when the sun's not doing a lot for us. And so the prices are very high and the reliance on gas and coal-fired generation is higher. So if we can help heat pumps to pull down those peaks, we are going to be disproportionately saving gas, coal, and also reducing the scale of the electricity generation infrastructure that we need for those peaks and increasing the average utilisation of our electricity infrastructure, which reduces the overall cost of electricity. So there's quite a bit of good opportunity there. Another thing we're finding is that the Australian building regulations and rating schemes typically focus on annual energy use. This graph is some work that I did. It was published in the ERA magazine, Equilibrium, recently. This is a sample of 60 office buildings in Sydney, doing the correlation between the peak electricity demand and the annual electricity consumption. And you can see that for a given level of annual consumption, there can be quite a big gap, variation between the lowest peak demand and the highest peak demand. So we don't have data to explain to us what the factors are, but I suspect it's because if you have a building with a very good thermal envelope, it will have a lower peak demand. If you have lots of glass and you're relying heavily on an efficient chiller system, then in extreme conditions, you'll have a lot of heat to get rid of and the chiller will be less efficient. So I think we can, if we do some research, we may well find that this is actually a big issue and a big opportunity. So I met last week with the people from Neighbours and they're actually looking at how can we do a rating scheme that will focus on reducing peak demand. So we might be getting somewhere there. Geothermal's got to compete with a lot of other things. So I don't want to just say, look, guys, it's going to solve everything. There's a competitive environment out there and there are a lot of barriers which haven't all been discussed so far this morning. So we are improving buildings. We are getting cheaper sensors and monitoring and data analytics and all these things which can help with geothermal, but also helps everyone else who's competing with you. Heat pump improvements, we're just seeing a revolution. Higher temperature outputs, understanding that if you cascade heat pumps, each one runs more efficiently and the overall efficiency is better, but you're paying for 2 heat pumps instead of 1. We're dealing with refrigerant impacts because of the global warming impacts. And we're also shifting away from inefficient distributed systems with poor insulation and poor control to a lot more point of use or local systems, because while you can do good distributed systems, there are lots of very badly insulated and very badly maintained ones that are running at stupid temperatures. Again, we're also seeing a revolution in batteries, and the Australian government's just brought in incentives, and batteries, in a sense, compete with managing heat pumps effectively. So this is my last slide. So the thing is that geothermal, as you've heard already this morning, is innovating and being creative. And this is just one example that I came across a few weeks ago of directional drilling, where they've learnt from the fracking and oil industry. And it means you can have a very small footprint and get enough access to enough ground source temperature energy to be able to more cost effectively drill. So this could be a retrofit or something like that. And they actually showed an example where they actually had the drilling machine in an underground car park of an existing building, drilling all the wells. So again, that's great to see. And there are lots of other things, and others have mentioned there's water bodies of all kinds. We can utilise exhaust air, which is not so much a geothermal one, but exhaust air, waste heat, you might as well use it. And geothermal may be a useful way of storing and transferring it. One fun thing is heat pump hot water service. There's one at 530 Collins Street, which is actually an air source heat pump in an underground car park. And the interesting point there is that the peak demand for this is early in the mornings when all the bike riders arrive and have showers. So basically the underground system is accessing lots of geothermal temperature, but also all of the cars that are arriving, the engine heat is being fed into the underground car park as well, which is cute. So again, I think there's lots of flexibility once we start thinking about this broader thing, that what we're trying to do is find ways of minimizing the inefficiencies of having variable and high temperature differentials, and geothermal certainly can do one of those things.
Thank you very much.